Welcome to the Explainer. Today, we're basically becoming cartographers of calculus. We're going to learn how to map the highest peaks and the lowest valleys of these complex mathematical surfaces. We'll break down all the essential tools you need to find any extreme point on any kind of terrain. So, let's start with the big question. You're looking at a 3D surface, right? How do you actually find the absolute highest peak or the lowest, deepest valley on something like this? You can't just eyeball it, that's for sure. We're going to need a systematic, mathematical way to pinpoint those exact spots. And to answer that, we're going to frame this whole journey with a cool explorer's metaphor. Think of it like this. Our mission is to map a totally new and complex landscape. We need to identify all of its key features, from the highest mountains right down to the deepest canyons. Okay, first things first, let's get our language straight. These points we're hunting for, whether they're peaks or valleys, have a collective name, extrema. And if you're just talking about one of them, it's an extremum. Simple enough. Now, our mapping missions are going to fall into two main categories. On one hand, you've got unconstrained optimization. Think of this as exploring a huge open world. The goal is to find every single local hill and valley out there. Then you've got constrained optimization. This is totally different. It's more like being asked to survey a national park and find the one absolute highest point, but only within its specific fenced-in borders.
All right, let's get our hands dirty with our first mission, exploring that big open world. Our goal here is to use our calculus toolkit to find every local peak, every little valley, and even those really tricky things called mountain passes that are scattered all over an unbounded surface.
For this kind of open world exploration, our go-to tool is the second derivative test. It's this super reliable 3-step method that lets us not only find potential extrema, but also figure out exactly what kind of feature each one is.
So, step 1. We gotta find all our candidate locations. In calculus speak, these are called critical points. Just think of them as the perfectly flat spots on our map, where the gradient is 0. I mean, these are the only places where a smooth hill could ever top out or a valley could bottom out.
Okay, next up, for each of those flat spots we found, we deploy a special tool. It's called the Hessian determinant, or just D for short. The best way to think about D is like it's a high-tech terrain scanner. It measures the curvature of the surface right at that critical point, and that data is what we need to classify it.
In this table right here, this is basically our decoder ring. It tells us how to read what the scanner's telling us. So if D is positive, the curvature is consistent. It's either going to be a bowl opening up, that's a local minimum, or it's a hill peaking, which is a local maximum. But if D is negative, well, then we've got something else entirely. And that something else is what's called a saddle point, which is just a fascinating kind of feature. It's a critical point, but it's not a max or a min. It literally curves up in one direction and down in another, exactly like a mountain pass, or, and this is a brilliant analogy from the source material, a Pringles chip. Okay, let's switch gears and move to our next challenge. Here, the rules of the game totally change, because we are no longer in that wide open world. Now, our job is to find the absolute, undisputed highest and lowest points, but only within a strictly defined territory.
And this slide just illustrates that key difference perfectly. Remember, with local extrema, we wanted to find all the interesting points on an open map. But with absolute extrema, we're inside a fenced-in, bounded area. Our goal now is to find the single highest peak and the single lowest valley, the absolute champions, nothing less.
So to do this, we can't just use our old test. We need a more complete algorithm. We start by finding any of those flat critical points that are inside our park. But then, and this is key, we have to meticulously check the boundary, the fence itself, for high and low points. And if that boundary has sharp corners, you bet we're checking those too. Finally, we just compare the elevations of all these candidates we've gathered to find our winners. So here's the crucial takeaway. We can't just look for those flat spots anymore. The highest point in our national park might be a nice rounded peak right in the middle, but it could just as easily be some random point on a cliff right on the fence line, or even at a sharp corner of the boundary. We have to check everywhere.
But what if our mission gets even more specific? What if we're not surveying a whole area at all? What if we have to stick to a very particular winding path or trail? How in the world do we find the highest point then? This is exactly where Lagrange multipliers come in. It is a really clever method designed for this exact scenario, finding the highest or lowest points of a function when you're subject to a constraint. So think of it as finding the highest elevation you reach while hiking on a predefined trail. It's a game changer in fields like economics, where you might want to maximize happiness given a limited budget. So the way this method works is by finding the exact spots on our trail where the gradient of the surface, the direction of steepest ascent, is perfectly parallel to the gradient of our trail. At that point of tangency, you literally can't get any higher or lower without stepping off the path. And hey, here's a fantastic pro tip straight from our source material. This could save you a ton of work. When you're solving that Lagrange system, you see that little lambda symbol? It's just a helper. The real goal is to use the equations to find a relationship between your variables, x and y. So don't get bogged down trying to find the actual value of lambda itself.
So after our expedition across all these different mathematical landscapes, let's just step back for a second and recap the really powerful set of tools you now have in your calculus toolkit. You can pretty much map any surface you might encounter now.
You've got 3 distinct, specialized tools. The most important thing is to first identify your landscape before you even start. Is it a huge open world? You're going to use the second derivative test. Is it a fenced-in national park? That's a job for the absolute extrema algorithm. And if it's just a single winding trail, then Lagrange multipliers are your absolute best bet.
Look, at the end of the day, this whole process isn't just about memorizing formulas. It's really a framework for systematic discovery and optimization, and it's applicable in so many fields from physics to economics. So the real question we want to leave you with is this. Now that you have the maps and the tools, what new mathematical landscapes are you going to explore?